what's so great about being normal? One of the things that we want to talk about in this question is standardized comparison and the Z-transform. And there's not a whole lot that we need to discuss, but why this normal distribution is so useful is if we have the case that our data actually fits to a normal distribution, is modeling something that's a normal distribution, we can compare things which look very dissimilar very easily. In other words, here we have two data sets. And I'm gonna plot these two data sets by themselves. And you can see these two data sets are visually very different. And we can't quite figure out how to compare these two data sets. If I were to look at these two data sets and I were to be able to affirmatively say, these are definitely normal distributions, and that does not mean eyeball it and say, it's bell-shaped enough, good enough, but go through an actual statistical process to assert this is definitely a normal distribution, then I can see comparing them like to like is a little, or comparing them one against the other is a little bit hard. And in fact, if I were to compare like a single value that I capture from one against a single value in the other, it might be a little bit tricky to compare them because you can see they're not at the same center point and they have a different spread. What I can do with a normal distribution is I can perform a Z-transform. I can take each of these values and I can remove the mean and I can divide it by the standard deviation. And when I do that, it'll force what the mean and the standard deviation of these distributions are. In other words, if I take the original data set and I take a look what the mean and the variance of these data sets are, they're different because these data sets are centered around different places and they have different spreads. Very different means and very different variances. But if I demean them, I subtract out the mean, and I divide by the standard deviation, you can see I can force the mean to be 0 and I can force the variance to be 1. I can force the standard deviation to be 1. This is a process called computing the Z-score, performing a Z-transform. And where this is useful is, let's say we've captured two measurements, and those two measurements are captured on different scales, and those two measurements are centered differently, and we want to figure out something about these two in terms of not describing one of them, but describing a comparison between the two. An example that comes up very often is the SAT used to be scored on 1600. Now it's scored on 2400. And the ACT is scored on, I believe, out of 24. And if you were to have taken the old SAT, the new SAT, and the ACT, and you were to know that, for whatever reason, the test takers, I guess, are independent and we're summing them up, and central limit theorem maybe says that this is probably going to be a normal distribution, but we'll take it for granted that it's a normal distribution. We might say, how do I compare a score on the new SAT against a score on the old SAT against a score on the ACT? They're centered at different points, and they have different spreads. How do I compare them? Well, what I can do is I can Z-transform them, and I can compare them like to like. I can turn their means all into 0 and their variances all into 1, and all that's left is details about this distribution. And so, in other words, if I had these two data sets, and I were to just select one possible value from each of these data sets, and I wanted to compare these values against each other, -7 and -13, is -7 from one test versus -13 from another test, or -7 from one data set versus -13, which is better, which is closer to the mean, which is above the mean, which is more of an outlier? It's very difficult for us to describe this. And we can compute the mean on these two data sets, and then we can say, oh, well, the mean's about 2 for one of them, so -7 is pretty far away from that 2, and the mean is 7.7 on the other one, and -13 is much further away. But wait, is S1 really way further away from the center than S0? If I computed the standard deviation, I could look at what the average spread is, and I can say, oh, these actually have kind of the same clustering. They're kind of about 9.5 for the standard deviation of one and 9.6 for the standard deviation of the other. But if I take this S1 and S0, and I compute and I run them through this Z-score Z-transformation, namely I demean them and I divide by the standard deviation, what I can say is S0 is about 0.94 standard deviations from the mean. S1 is about 2 standard deviations away from the mean. In fact, this S1 value is clearly way more of an outlier than this S0 value. And if I were going back to my SAT example, this could be the case where I could say, oh, you're actually clearly better on your SAT scores, you're on your ACT scores, because they are much further away from where the mean is. You're in the 99th percentile. You're this many standard deviations away from the mean versus that. And it's about comparing these distributions, comparing values with these distributions, as long as those are normal distributions. This is why that normal distribution is so useful, because it has these properties and it has this clear, intuitive, simple, closed-form mathematical formulation.